Hey everybody, welcome back to part two of computer number systems. So the next topic I'm going to be covering in this section is unsigned and signed arithmetic. So the previous video was unsigned conversions. So we did a couple of examples of those. I'll cover both signed and unsigned arithmetic, and then the last video for computer number systems would be signed conversions, since there's a lot of examples we have to go over for that. And then I'll probably just have one video for computer floating point operations and then computer architecture and organization. I'm kind of just making it up as I go, but I'm trying to pick out really good examples for you guys so that you guys um, understand like how signed and unsigned work and everything, because your exam will have multiple questions on these things. So again, I do encourage you guys to check out the practice problems because those practice problems will be on your exam, and there's no better way of studying than just practice. But these videos are just in case you feel stuck. So hopefully these clarify any questions you guys have. All right, so let's get started for this video. First thing we're gonna do is unsigned arithmetic. And we're going to do unsigned arithmetic for hexadecimal first. Okay. The first example I want to do, and again, these are in your practice problems. I'm going to do dB plus 42. And remember, these are hexadecimal numbers, right? Okay, so here we can just add like normal, like if it was a regular decimal, we'll add the first two first. So the first thing we want to do here is b plus 2. And remember in the previous video, I told y'all that b is represented by 11 because a is 10. And I'll kind of just rewrite this as a reminder. Okay, so this would be the equivalent, sorry, it's super ugly. This would be the equivalent of saying 11 plus 2, which is, what is that, 13, right? So we said 13 is D. So B plus 2, that's going to be D. And then you can also, it's kind of intuitive because B and the next is C and the next is D. So that's kind of how like you move over, right? Okay, now let's look at this part. D plus 4. All right, so D we said was 13 plus 4. Oops. That's gonna be 17, right? And that's actually a problem because 17 doesn't fall in the range of hexadecimal. Remember, hexadecimal is base 16. So what we're gonna do here is just subtract 16, and we're gonna get 1. And then we'll bring the D down, so this is our answer. But that subtraction we did, we had a remainder of 1, so we do have overflow here, right? So we would put that in the next bit. So we have like that one bit kind of being cut off, right? So here it'll ask you if there is overflow, and since we had that one bit, we'll say yes, there is overflow. Yeah, hopefully that makes sense to you guys. Mm, okay, let's do another example. We'll do AB plus 43. Okay, B plus 3 is going to give us E. Remember again, this is just 11 plus 3, which is 14, which is E. Right, no issue here. It falls into the range. We don't have to carry any bits over, so we can just leave that like that, right? The next one, however, we have, remember, A is represented by 10. So this would be 10 plus 4. 10 plus 4 is 14, which is, we already said E, right? And that falls within the range. There is no extra bits over here, so there is no overflow. Right. Okay, yeah. So for unsigned questions, we're looking to see if we have extra bits that get pushed over that don't get included. Only for unsigned does this apply, right? So yeah, that's kind of how you do hexadecimals first. So let's move on to binary. And remember, we're still doing unsigned. Yeah. Um, okay, so let's do this example. Okay, and the way this works is, remember our bases only go up, we only have two bases, so we can only have ones and zeros, right? So it's not like regular addition. If you add a one and a one, you get a two. That's not how it works. So first we'll just add like normal. So 0 and 0 is going to be 0. 1 and 0 is 1. 0 and 1 is 1. 1 and 0 is, oh, sorry, that should be also 1. 0 and 1 is 1. 1 and 0 is 1. Okay, so here is our first problem. So we have 1 and 1 equals 2, right? But we can't have the number 2 in our binary. It doesn't work like that. It's only ones and zeros. So what we'll do is we'll mark it as a 0. Oh, sorry, I think it stopped sharing. Okay, but anyway, so yeah, so we have 1 and 1. Since that goes over the base, we'll mark it as 0 and then we'll carry the 1 over. The problem here though is now we have 1, 1, and 1. So when we had two ones, we made it a 0 and then we carried the 1 over here. But now since we have three ones, we'll make it a 1 and then we'll have to carry the 1 over. However, this bit gets lost, right? Because there's nothing to add it to. I can't add it to anything. So I'll keep this how it is, but I need to mark this as yes, overflow, since we had that extra bit still left over. Yeah, so hopefully that makes sense. Okay, let's move on to our next example I have for binary. That's going to be 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1 again, 1, 0, 1, 1. Okay, and let's add that. 0 and 1. It's 1, 1, and 1. Remember, we're going to make that a 0 and carry the 1 over. So this just becomes 1 plus 0 plus 0, which is 1. 1 and 0, again, make it a 0, carry the 1 over. Now we have three ones, right? So remember, like I said over here in this example, we're going to drop the 1 here and then carry the extra 1 over here. So this becomes 1 plus 0, which is 1, and then the rest are just zeros. So luckily we don't have any bits left over here. So this means that there is no overflow. So again, whether it be hexadecimal arithmetic or binary arithmetic, you're looking to see if we have any remainders left over that don't get to be added, right? So the actual answer, you'll leave it as is and then um, not include that extra bit on the side, but you'll still need to mark it as overflow. Exactly. Okay. So yeah, that is unsigned. Luckily, those are super easy to tell whether there's overflow or not. We're just looking for the extra bits being carried over. But the story is different for signed. So let's go ahead and do signed hex arithmetic first. Alrighty, so since we're working with signed values, we need to pay attention to whether or not these hexadecimal numbers fall into a positive or a negative range, right? So the way we're able to tell if a hexadecimal number is positive or negative is simply the number it starts off with. So the first half of the hexamal, the first half of the range of hexadecimals, remember that the range is from 0 to 15, or that's the same as saying 0 to F even, right? So we'll divide this by 2, and then we'll get 7, right? First half is going to be positive. Second half is going to be negative. Okay. So that being said, if I had a number like 0, 7, we look at the first digit and we say, okay, does this fall into the positive or the negative range? This 0 indicates that this number is positive, right? But if I had, let's say I had E, F, I take a look at that first number again. Does it fall in the positive range or the negative range? Here we know that E is in the negative range, so this number is negative. Okay, so why am I telling you this? Like, why is this important for y'all to know? This is important because we want to be able to tell if there's overflow or not. And previously, when we took a look at unsigned arithmetic, the way we were able to tell if there's overflow is if we had an extra bit being carried over, right? But if that happens in the case that we have two signed numbers, we don't care at all if there's leftover bits. We don't care at all. So we can have a leftover bit and then it could still be no overflow. Um, how we're able to tell if there's overflow or not is based off of positive and negative numbers. So we know that regularly, if we had two positive numbers together and we added them together, we would also get a positive number, right? And then we know if we added two negative numbers, we should also get a negative number, right? And then if we had a positive and a negative, well, then it could be either or, right? So there will never be overflow in that situation. However, if we get a positive and a positive number and we end up getting a negative, that is an indicator of overflow. right? And same thing for negative. If we have two negatives and we end up getting a positive, that's also an indicator of overflow. However, if we have that positive and a negative, it doesn't matter what sign we get. There will never be overflow in that case. So that's important to know. That being said, let's move on to our first example. Our first example is going to be 54, and remember, this is hexadecimal. 54 plus 82. So we'll add this like normal. 4 plus 2, that's going to be 6. There's no need for me to carry any other numbers over since that falls into the range. Right, and then 5 and 8. Well, let's take a look at these signs. So 5, we know that falls into this positive range. So we know we're having a positive number. And then this 8, that falls into the negative range. Right? So we know that no matter what sign we end up here with, there will never be overflow. So we can already tell no overflow. Okay. And then let's just add like regular. So 5 plus 8, that is going to be 13, which is the equivalent of D6. So that's the answer. It's going to be D6 with no overflow. Okay. Let's look at the next example. We have E0 plus AE. Oops. Let's take a look at this. So since these are both letters, we already automatically know that's going to be in the negative range, right? So we have a negative plus a negative. So theoretically, we should also get a negative. If we get a positive, then we know that there's overflow. Okay. So 0 plus E is just going to be E, and then E plus A. So E is represented by 14, and then A is 10. So this equals 24. However, that's not in the range of hexadecimals. It doesn't fall in base 16, so we're going to subtract base 16 by that. And so 24 minus 16, that should be 8. And the answer, and E we just bring down, right? So even though we have leftover bits that we should have on this side, we still got a negative, right? Because 8 falls into that negative range I was talking about over here. So even though we have extra bits over here that we should bring over, there is no overflow because we still get a negative. So really, it doesn't matter about like the bits you have out here. It doesn't matter. The only thing that matters is if the signs are correct. And that's the difference between unsigned and signed, right? Okay. So that is hexadecimal. So now let's do binary. So same rule applies. We'll take the range of numbers, which is only 0 and 1 in this case, remember, because it's binary. There's only two numbers we can have, but we'll half it. First half, which is 0, is going to be positive. Second half is negative. Right? So if we see a number start with a 1, then that is an indicator that that number is negative. It starts with a 0, the number is positive, right? Same rules apply, positive plus positive, we should get a positive number. Negative and negative means we should get a negative number. And then if it's a positive and a negative, we'll never have overflow. Okay, so let's start off with our first example. Okay, so 1 plus 1, remember how we said that becomes 0 and we carry a 1 over? 1 plus 1 plus 1, that's 1, carry a 1 over. 1 plus 1, 0, carry the 1. This is just 1, and then 0, 1 plus 1. That's going to be a 0, carry the 1. 1 plus 1, 0, carry the 1. 1 plus 1, 0, again, carry the 1 over here. So we have that remaining bit. But again, this is signed. It doesn't matter. Let's pay attention to the signs. So we already knew that we had a negative number, again, because this is 1, we know that's negative, and a positive number. So, and then we ended up getting a positive number. But remember, like I said, that doesn't matter. If we have a negative or a positive number, there will never be overflow. So the answer to this problem is 0, 0, 0, 0, 1. Wait, 0, 0, 0, 0, 1, 0, 1, 0. Yes. But there is no overflow, right? Even though we had that bit, there's still no overflow because we have a negative and a positive number, meaning there will never be overflow. Okay, now let's take a look at the next example, and this will be the last example for arithmetic. Okay, so let's look at the first leading numbers. Looks like we have two positive numbers because they're both zeros. So theoretically, this sum that we get should also start with a 0. If it starts with a 1, then we know that there was overflow. Okay, so 1 plus 1, that's a 0, carry the 1. 1 plus 1, again, 0, carry the 1. 1, 1, 0, 1. We have 3 ones, so we'll drop the 1 here and then carry another 1 over. Ooh, okay. Look at this. So we ended up getting actually a 1 in the beginning. So therefore, there is overflow in this example. So this is the answer, and there's overflow. All right, so that's the end of this video. Again, just to mention, when you're working with unsigned numbers, how you tell if there's overflow or not is if we have extra bits coming over on the side, right? If it doesn't fit in the range, right? And again, when you're answering the question, don't try to include that extra 1 over here. Leave the answer as is, right? We never want to write this extra bit anywhere, right? We're only caring about that so that we can tell if there's overflow, right? But for signed, the extra bits don't matter at all. The only thing that matters is if the signs match up. So again, if you have a positive and a positive, you should get a positive number. Negative and negative, you should get a negative. And if you have a positive and a negative, well, there will never be overflow. So yeah, that's the end of that. Next video I'm going to do for computer number systems is going to be signed conversion. So stay tuned for that.